Now, I always thought if I wasn't a teacher, I'd probably be a lumberjack. And as you can see by this demo right here, I definitely got the chops to do it. But I didn't do this for my love of lumberjacking. I did this to demonstrate an important concept. As you saw here, when I chopped this wood with this beautiful trusty axe right here, I was able to split right through it. This demonstrates what we're going to talk about in today's lecture, which is shear stress, which is the phenomena created when a material splits relative to itself right down the middle. And today we're going to explain and explore this concept in further detail and go over a variety of different example problems that really help demonstrate what this topic is all about. What we're going to talk about in today's lecture is two things. We're going to continue our conversation about safety factors, which is what we introduced last time. But in this lecture, we're going to introduce the concept of shear stress and really explain what that's all about. Now, if you watch the video in the beginning, you'll see when I threw the axe down towards the wood, there's a downward force of chopping from the axe. That piece of wood splits right in the middle, but realistically, it's trying to fight that and it's providing force going up. Now that is what shear is. And shear stress is the stress that's developed because of the shear force experienced inside of our beam. Or, in this case, stump. So just as a review from last time, safety factor is a way that engineers kind of mathematically interpret how safe their system is. You calculate it by taking the max limit of your material, and you divide that over top of what you design your system to hold. Ideally, your numerator will be greater than your denominator so that your system has an abundance of safety. As we explained before, stress is all about the internal stresses experienced in our system. We've already discussed normal stress, but now we want to start to look at shear stress, which, as I've explained, is going to be the stress developed due to the shear force over the cross-sectional area of our material. Now, a good way to kind of think about this is imagine you took that beam and you chopped it up into a bunch of little sections. Each of those areas is going to be experiencing a shear force. The shear stress is going to be the shear force divided by that area. Now, I don't know if it's just me, but when I look at this looks very familiar to me. This idea that we've taken a beam and we've chopped it up into smaller parts. What could this be? It looks just like a good old Hershey bar. And boy, do I love chocolate. That Hershey bar looks pretty tempting right now. I think I gotta grab it and have a snack. Boop! Hershey bar! The magic of PowerPoint. Really, what this Hershey bar is meant to represent is a concept of shear stress. We all know when you look at the Hershey bar, you can see these smaller ridges right in the middle, right there. Not only does it help the Hershey bar look cool, but this is actually a very useful tool that the engineers, or chocolate makers at Hershey, used to help you get access to your Hershey bars. Now, what do I mean by that? Really, shear stress is going to be the shear force divided by the cross-sectional area. So what we know is that you wouldn't want to just have a giant bar of chocolate with no little indents like a Hershey bar, because if you did that, it would be almost impossible to break off uniform pieces of the Hershey bar. By putting these lines in, what the Hershey chocolatiers have done is they've decreased the cross-sectional area at those particular points. And if you look at this particular example or formula right here, if you lower the area, then what you're doing is you're increasing the shear stress that'll be developed in that particular spot. So as a result, it actually becomes easier to snap your Hershey bar at that particular point. So on our Hershey bar, where the area is smaller, when we apply a force here, we're going to concentrate the stress along these particular points. And what should happen is that the Hershey bar should snap right exactly in the area where we have less chocolate. And that is a delicious and real-world example of shear stress. Hershey's chocolate. That's what it's all about. So, shear is just another force that our material is experiencing. The shear stress is just the shear force divided by the cross-sectional area of that material. And it's represented by the symbol tau. Again, just to review, the units of shear stress are going to be the same as normal stress. Our stress is just pressure, it's force over area, so it'll be either units of pascals or psi, pounds per square inch. Let's do an example problem now. What you can see is we've got this yoke and rod connection, which is pretty much just two cables, and a pin system that's holding those two things together. And what the question asks us is if this system is subjected to a tension force of 5 kilonewtons, what is going to be the normal stress developed in our 40 millimeter rod? Now this is normal stress. We've already talked about this. So let's jump to a handwritten solution and calculate the stress on the rod. Let's take a look at this problem now, which combines both normal stress and shear stress. What we can see is we've got this system with two rods or two cables on either side. We can see that the rod is experiencing a 5 kilonewton tension on either side. It's 40 millimeters in diameter on the left side and 30 millimeters in diameter on the right side. And we've got a pin holding these two cables together that has a diameter of 25 millimeters. Now something I always hear people get confused about is the fact that we've got a 5 kilonewton force on both sides. People think, wait, why is that not 10 kilonewtons of tension that this whole thing is experiencing if we have 5 and 5? Well, what's actually going on is that this is just a Newton's third law action-reaction pair. When you pull on this cable with 5 kilonewtons, as long as the other side doesn't move, it has to pull back with 5 kilonewtons. Therefore, it's just someone's pulling with 5 kilonewtons this way, and the cable reacts accordingly. Consider this piece of paper here as another example. If I push down on this piece of paper with 1 Newton of force, well, the ground pushes back up. Well, not the ground, but the table pushes back up with 1 Newton as well. So the paper is experiencing 1 Newton from me and 1 Newton from the table, but we don't say that that's experiencing 2 newtons. We say it's only experiencing 1 Newton of compression. So that's what's going on here is it's got 5 kilonewtons of tension. So to solve part A, we need to determine the average normal stress in the 40 millimeter rod. Now normal stress is represented by sigma, which we say is force over area. Now we already know the force that this side is experiencing. We know that it's experiencing 5 kilonewtons of tension, which I'll say is 5,000 newtons. And what we don't know is the area, but we plug that in. That's pi over 4 times the diameter of 40 millimeters squared. Now the units we're going to get out of this are newtons per millimeter squared, which turn out to actually be megapascals, or 1 times 10 to the 6th pascals. This is a cool trick with units. That way you don't have to convert this to meters and then back into other things. You can just do all your math real quick and get megapascals out. And let me show you exactly why this kind of works. So what we can see is that 1 pascal is force over area and is usually 1 Newton per meter squared. We know that 1 meter squared can be represented by multiplying 1,000 millimeters, which is 1 meter, times 1,000 millimeters, which is also 1 meter. So this tells us that 1 meter squared is equal to 1 times 10 to the 6th millimeters squared. So what I can do is I can rearrange this equation right here, and I can say that 1 pascal is equal to 1 Newton per 1 times 10 to the 6th millimeters squared. What I can do is if I multiply both sides by 1 times 10 to the 6th, this becomes 1 times 10 to the 6th pascals is equal to 1 Newton per 1 millimeter squared. And that's why 1 Newton per millimeter squared gets us the units of megapascals, or 1 times 10 to the 6th pascals. This is a really good little trick right here that I think makes solving some of these problems a little bit easier because you don't have to convert units. Anyway, back to this part right here. We've got 5,000 newtons over pi over 4 times 40 millimeters squared. Again, we're getting this answer in megapascals. And what we get is that the normal stress is equal to 3.98 megapascals. Now that we've solved for the normal stress in that rod, let's look at the shear stress developed in the pin. Now the pin is going to be the thing that's experiencing shear stress, because if you look at a picture of the pin, the dotted line represents the pin that's inside of the yoke. So essentially what's going on is when you pull with this 5 kilonewtons, the pin can break in two particular spots. It can break right here or right here. It's those particular spots that the pin could whoosh, snap in half and break apart due to shear. So it's at those two spots that our pin is fighting back with a shear force of V. Now this is a very important concept to understand. Because our pin can break in two spots, it's going to have two shear forces fighting back. And as a result of that, we call this double shear. So double shear really just means you've got two shear forces fighting back. Let me illustrate what that means a little bit more with this diagram. In shear stress, it's always important to understand whether you have single shear or double shear. Now the example on the right is what we just talked about. It's a system that would be in double shear. And the reason that system is in double shear is because if we've got 3 sticks, one in the middle and 2 on either end, and we try and pull this system apart, what would happen is that the glue on the top and bottom piece of that wood would fight back. So we'd have two forces fighting the one pulling force. Those would both be shear forces, and we refer to that as double shear. An example where we have single shear is the picture on the left. And this we refer to as being in single shear because there's only one force that's fighting back against the force you're pulling with that prevents that material from whoosh, splitting apart. So shear is all about the material splitting or sliding relative to itself or the other material that it's attached to. So it's always important to understand single shear versus double shear. And as you'll see, a large majority of problems that we do tend to be double shear. And this actually is beneficial in the real world because if you've got double shear, it increases the structural strength of your system. In single shear, V would be equal to F because we have only two forces in the x direction. As a result, tau would be V over A. So just our basic equation for shear stress. In an example with double shear, we would do a sum of the forces in the x direction. We would find that 2V equals F, or that the shear force, V, would be equal to force over 2. As a result, what this gets us is that our shear stress is going to be equal to V over 2 over A, or another way that people sometimes like to think about this is that it's the shear force, but now we've got 2 times the area of glue in this example. So tau would be V over 2A. Both of those things are equivalent, but ultimately what you see is that because 2 is on the denominator, the shear stress that's experienced in this material is half of that as what the shear stress is in single shear. And that goes back to explain why our structure is much stronger if we can put it in double shear than if we can put it in single shear, because the stress that will be developed inside the material will be half as much. Now that I've explained that concept a little bit more clearly, let's jump to a handwritten solution where I show you how to solve for the shear force inside of this pin. Now we can look at part B, which asks us to solve for the shear stress in the pin A between the two members. Pin A is going to be experiencing what we call double shear. And I think I showed that on the PowerPoint slides. So what we can do is we can set our tau equal to the shear force divided by the area. Because we have double shear, which I'll draw a little diagram for right here. So what you can see is that double shear effectively means that we have 2 shear forces fighting back against the 5 kilonewtons. The reason this is the case is because our bolt, or pin, has 2 junctions, one right here and one right there. It's possible that right there and right there the bolt could split. So both of those pieces of the bolt are fighting back. Now what this results in is that if we do a sum of the forces in the x direction, we'll find that if this equals 0, we have 2v to the right minus 5 kilonewtons. Therefore, the shear force involved in this pin is going to be equal to 5 over 2. kilonewtons. Not too hard. So what we say then is that our tau is the V, or the shear force, which we just said is 5/2 kilonewtons, or 5,000 newtons, divided by 2, divided by the area. Well, the area of our pin is pi/4 times 25 millimeters squared. And again, what you'll see is we have newtons per millimeters squared. So the answer we get out of this question right here is that our tau is going to be equal to 5.09 megapascals. There you go. Now let's look at this example here. What we've got is an eye-shaped piece of wood, and it's attached by two claws that are pulling it apart at either side. What we're asked to determine is a couple different things. If we know that the specimen is subjected to an average normal stress of 2 ksi, the first question asks us to solve for the axial force in this particular specimen that's being applied. So let's jump to a handwritten solution and show you how we approach this problem. Here what you can see we have is another question that involves both normal stress and shear stress. We have an eye-shaped piece of wood that's held together by these two grips on either side, and we're exerting a force P to the specimen. Question A asks us to determine the axial force P that's applied to the specimen. And we can see that the specimen is in tension. So we're told that the specimen achieves a normal stress of 2 ksi. So for part A, we're going to have to use the normal stress data we get to determine the P that's being experienced. We know that normal stress is the force, in this case P, over the area, A. What we can see is that our cross-sectional area over here is going to be equal to 2 times 1 inch. The thing that we don't know is the P, but we do know that our stress is 2 ksi. So we can do one of two things. We can either leave this in ksi and get our answer in kips, or we can convert this to psi and get our answer in pounds. So let's just do that. Let's just say that this is going to be 2,000 psi. This tells us that P is equal to 4,000 pounds, or 4 kilopounds for kip. Same answer. So that's how we solve for part A. The second part of this question now is going to deal with shear stress, and it's going to ask us to calculate the shear stress developed along segment AA of our specimen. And segment AA, it's a little bit hard to see in this picture here, so I'm going to show you with the highlighter, but it's more or less right here along that material. So let's jump to a handwritten solution and figure out how to calculate the shear stress in that piece of our testing specimen. And just to help you visualize what's going on a little bit more clearly, if we look at our testing specimen, what we can see is that the P is going to be pulling it apart, and that the middle of our eye shape is attached to the two junctions on the outside via itself. As a result, this problem is going to be double shear. And we're going to explain in the handwritten solution how we go about calculating this. Part B asks us to find the average shear stress developed along section AA of the specimen. Section AA is up here in this particular spot right there. So what we can see is that piece of the wood is actually also going to be in quote-unquote double shear. So the reason that's the case is because if we look at this eye-shaped beam, which I'll draw right now, we can see we have the eye-shaped beam. It's being pulled on either side with P, which we just determined was 4,000 pounds. And because the beam is held with these special grips here and it's in an eye shape, we can see that if this beam failed, this piece of wood would split on these two pieces right here, these two dotted lines. So because that's the case, that means we have two pieces of wood effectively that are fighting that, and we have two shear forces as reaction forces. This is, quote unquote, as we like to say, double shear. So if this is double shear, then what this tells us is that the sum of the forces in the y must be equal to 0, is going to be P minus 2V, or it's going to give us that V is equal to 2 over P. To compute tau, which is the shear stress, we say that that's equal to the shear force over the area. Well, we now know that the shear force is P over 2. Whoops, I don't know how I did that. It's equal to P over 2. So that gives us 4,000 divided by 2, divided by the area. Then we can see that the area is this piece right here is 4 inches tall. And we can see that the depth of our material is 2 inches. So that's kind of this depth here. It's a little hard to see in this picture here. It's more clear on the PowerPoint slide, I'm sure. But our area is going to be 4 inches tall by 2 inches in the other way. And this gives us that tau is 250 psi, because on the top we have pounds, on the bottom we have inches squared. So we get 250 pounds per inches squared, or 250 psi. There you go. Now, while this lecture has already been pretty funny and I've eaten some chocolate, it wouldn't be useful to learn all this material unless we could apply it to the real world. So put on your shoes and drive yourself to Home Depot, because we're going to build some fake structures. Now, everything you've just learned can help you build two different things in your own backyard. It can help you build a deck, and it can help you build a good old-fashioned seesaw. So let's figure out how shear stress can help us understand how we build these structures and make them safe. Let's say that you wanted to build a seesaw. So after you went online and you did some Googling, you found this advanced design below, which, I'm joking, it's not advanced, just a couple pieces of wood, and it looks like a steel bolt in the middle. But let's say that you decide to build this structure here. How safe is it? And what would be the maximum weight of people that you would allow onto the seesaw? Would it be able to stand and structurally remain intact? Let's jump to a handwritten solution and figure out how you can build your very own seesaw. Let's now apply everything we've learned to actually doing some real stuff in the real world. Hashtag building stuff. So let's say you go online, you Google some pictures of homemade seesaws, and you decide to build this one on the left because you're really bored and you got nothing else to do. So you go to Home Depot, you talk to my dad because he works there and he gets angry at you, but he helps you figure out what you need. And you purchase a 1/4 inch diameter steel bolt, and you go online, you do a little bit more research, and you find that that bolt has a maximum shear stress of 7,500 psi. If that's the case, and you want it to be safety first and make sure that you don't get sued by the people that play on your seesaw, what would be the maximum allowable weight of the riders if you wanted to give a safety factor of 2? So here I've gone and drawn a little tiny rinky-dink free body diagram of our seesaw. We can see that it's held together by a pin. We've got our piece of wood right there. That's kind of your pin right there. And what we know is going to happen is we're going to have the weight of person 1, the weight of person 2. And because it's a pin, we're going to have two reaction forces. We're going to have RAY and then RAX, reactions. So by doing a quick sum of the forces in the Y equation, you get that negative W1 plus RAY minus W2 equals 0. So RAY equals weight 1 plus weight 2, which we'll just call 2 times the weight if we assume that both of our people weigh the same amount. We know that this question is asking us to solve for shear stress, more or less. So we know that tau is equal to V over A. Now we know the area of our bolt already. It's a 1/4 inch diameter steel bolt. So we know that the area is just going to be equal to, well, pi over 4 times the diameter squared, which is pi over 4 times 0.25 squared. So that's our area. We have to figure out what V is. What is V? If we look at the side view of this seesaw and take a closer look, it'll become more clear. And let me draw a picture of that right now. So I've drawn a side view of our seesaw, and what we can see is we've got our 2 pieces of wood on the outside. our piece of wood in the middle, that is what people sit on, and we've got the bolt that's holding everything together. Now, because RAY is more or less the force that's being applied to the bolt via the seesaw, we see that our bolt can pretty much fail along these 2 points right here. So because of that, we call these 2 things our shear forces. So again, we have double shear. Therefore, a quick sum of the forces in the y over here tells me that negative RAY plus 2V equals 0. Therefore, V is going to be equal to RAY divided by 2. The last step of this question is to involve the safety factor, which is 2. So we know that safety factor is equal to 2 is equal to the max limit of the material over the actual real-world conditions. In our case, we know that the maximum shear stress is 7,500 psi. We don't know the real-world design, so what we need to know is that the actual limit for tau that we can experience in this problem is going to be 3,750 psi. So combining this section here with this piece of information and this piece of information, we can now solve by saying that tau limit that we have is 3,750 psi is going to be equal to V, which is RAY over 2. We know that RAY is 2W, so we're going to get that this is W divided by the area, which is pi over 4 times 0.25 squared. And again, just to kind of show this a little more clearly, because people might go, where did that come from? These 2 things right here lead to the fact that we get W on top right there. So now we can solve this for W, and we find that W max of each of our people on our seesaw would be 183 pounds. So the seesaw is definitely strong enough to hold some little kids, but if you had a couple adults on here, the bolt would actually split in half, which is pretty crazy to think about, that you could split a 1/4 inch bolt in half, but that's the answer we get. And there you go. Be safe. Try and choose a bigger than 1/4 inch steel bolt if you're going to have a couple of hooligans playing around on your seesaw. But that's how you apply all the stuff you're learning in this class to something in the real world that you actually could build yourself. Now that we've built a seesaw and done a little analysis there, let's look at another example where shear stress comes into play. Let's say that you want to build a deck in your backyard, because decks are great for parties. Oomps, oomps, oomps. And we decide to invite Andre the Giant, one of the greatest, most giant people in the history of the world, over to test our deck's strength. Let's jump to a written problem now and show you how I would solve this question. Let's take a look at another real-world type example. This problem assumes that you went to Home Depot, you purchased some materials to build a deck, but oh no, you forgot the bolts. The good thing was you had some wood glue lying around your house, and you figure that's probably good enough, because you look on the bottom and it says maximum shear strength is 1,250 psi. It's 1,000. Seems like a lot. So to build your deck, you glue an 8-foot long, which is this beam right here, 2-inch by 10-inch wooden beam between 2 4-inch by 4-inch wooden posts. We're told that the wood we bought has an ultimate strength of 7,000 psi. So basically, when I compress this piece of wood, it has a maximum normal stress of 7,000 psi. So there's 2 constraints that we have: the shear strength of the glue and the normal strength of the pieces of wood. Now, we've got our good friend Andre the Giant is going to come over and test our deck later on and make sure that it's sturdy. And when he comes over, he's going to say, "Anybody want a peanut?" And given that Andre the Giant is a massive human being, he's 7'4" and 529 pounds, question A is, would our deck be able to support him? And question B is, what would the factor of safety be of this system? So the first thing we need to do is draw a free body diagram of this system, and I'll do that right now. So we've got a makeshift free body diagram. I've drawn my Andre the Giant impersonator right here. He's 2 feet from the edge. What we can tell just by looking at this system is that we're going to have an RAY over here, an RAB over here in response to Andre the Giant's weight coming down at this particular point. Now, just by looking at this, we can already tell that RAY is going to be the limiting factor, and that this point right here is going to experience more of the weight. If Andre the Giant stood directly over here, this RAY would take all of his weight, and RAB would take none. So the closer he is to RAY, the more this takes. Therefore, RAY will be our limiting factor and what we need to solve for first. So the thing that we need to figure out is we need to do a sum of the moments about point B, set that equal to 0, and that's going to get us negative RAY times the 8 feet along the bottom. That's going to go clockwise, so we say it's negative. And then we have plus weight of Andre the Giant times his distance away, which we can see is going to be 6 feet. And we say that that's counterclockwise because Andre the Giant wants to rotate counterclockwise about this point right here. So what this tells us is that RAY equals 396.75 pounds. Now what we need to figure out is what's going on with the deck. Is it going to collapse due to normal strength failure of the wood, 7,000 psi in the posts, or is it going to potentially collapse due to the shear in the deck? So let's look at the shear first. And I'll just circle this right here. So we look at the shear. Looking at our side view, what we can see is that the weight of Andre the Giant, pushing down here, is going to be fought by two forces inside right here at the joints. And again, this tells us that this right here is double shear. So if that's double shear there, then what we have to do is we do a quick sum of the forces in the Y. We set that equal to 0. And that's going to tell us that pretty much the downward force, which was the weight of Andre the Giant and RAY, because his weight goes down on the beam, but it's felt over here as RAY. So sum of the forces in the Y is negative RAY plus 2V. Therefore, V is equal to RAY over 2, which gives us that V is 198.375 pounds. So we know that the area of the glue is going to be the area that's contacted right here. So the area of the glue is going to be equal to, well, it's a 4-inch wooden post this way. That's why we have this 4 inches. And we know that this dimension right here is, well, it's a 2 by 10-inch wooden beam. So the area of our glue is going to be 4 inches by 10 inches, which is 40 inches squared. So now our final step pretty much is to figure out tau. Tau we know is V over A, which is going to be the V, which is 198.375 pounds, divided by the area, which is 40 inches squared. This gets us that the deck is experiencing 5 psi at that joint right here. Now what we can see is that that is way less than the glue's maximum shear strength of 1,250 psi. So holy shnikes, our deck is awesome. It's so good. So the safety factor of our deck in this particular spot, and this is kind of like question B, we're jumping ahead. This is like A, tau on the first part. Now we're looking at what's the safety factor against shear strength failure. Well, the safety factor, if you recall from all of our problems we've done, is the max limit of the system over what's actually being experienced. So the maximum limit was 1,250 psi, and we're experiencing 5 psi. So the safety factor against this is a whopping 250. That's crazy. So what this means is that our deck could hold 250 Andre the Giants on top of each other at this point before it failed. At least the glue could. Now what we need to figure out is, what about this post? could that crush under his weight? So the second thing that we need to consider in this problem is the compressive strength. So now we're going to check compressive strength failure, and we're going to check the normal stress. We know that normal stress is going to be equal to the force over the area, which in our particular case, each of these beams is experiencing 1/2 of RAY. So it's experiencing 198.375 pounds. The reason being that when this is pushed down here, the RAY, the shear force is the shear force along both of these sides. Well, that shear force is going to be more or less the same force that's compressing this piece of wood. So the force that we have in the wood is going to be 198.375 pounds. And the area of this beam, they're 4-inch by 4-inch wooden posts. So this is going to be 4 times 4 inches squared. What this tells us is that we get a whopping 12 psi that comes out in compressive strength, which if we look at the maximum limit was 7,000 psi. So we're way safe. And just to confirm, we compute the safety factor against compressive failure, and we find that this is going to be the max limit over the actual being experienced, which is 7,000 psi, divided by the actual, which is 12, very dinky amount, and we get that the safety factor here is 583. Holy crap! So in order to break this piece of wood here, we would need to have 583 Andre the Giants stand one on top of the other, which that'd be really, really tall. So that probably couldn't happen. So the answer for what is the overall safety factor of the system is the lower of these two. So to answer part B, the overall safety factor of our system is 250. And the reason is because 250 is less than 583. So we always choose the lowest safety factor because that is the safest that the structure is. And there you go. Now you know that if you just want to build a deck, you can do it with wood glue and a bunch of wood, and it's going to be able to hold hundreds of your friends, and you'll be safe. But don't take my word for it, and don't ever come back and sue me if you find out that your deck didn't hold an Andre the Giant sized person. There you go. At the end of this presentation is a couple more example problems that I'm not going to go over, but that have solutions that help you practice this material even more. That's it for today's lecture. Hopefully you learned a little bit more about stress and shear stress specifically, and you learned how that applies to the real world. And hopefully now you've got a hankering for some Kit Kat or Hershey's, and you can go to the store and pick some up. I'll see you next time.
Give me a break, break me off a piece of that Kit Kat bar.
Wow, wow, wow. Double shear.
Whew. Damn. That's some of the best footage I ever shot. Students are going to love seeing me chop all that wood. Wait a minute. Was I not recording?